Welcome to this Prep 50 class on mathematics. And today's topic we have sets. This topic has been broken down into two sections. Section 1 will look at introduction to sets. We'll define sets and we'll look at the various types of sets and calculations involved. And in section 2, we'll be dealing with Venn diagrams. Section 1, Introduction to Sets. Introduction to sets, the objectives. At the end of this section, the candidates or the students should be able to identify types of sets, that is, empty, universal, complement, subsets, finite, infinite, and disjoint sets. These are examples of sets, that is, the types of sets. They should be able to solve set problems using symbol. They should be able to use Venn diagrams. Venn diagram is for the next section. So let's continue. Definition. A set is a collection of well-defined objects. The objects are called elements. That is the objects of a set. We said that a set is a collection of objects, and these objects are called elements. The elements can be anything, that is numbers, items, words, etc., anything, and they are usually displayed inside a pair of matching brackets, that's a pair of matching braces or coily brackets. We'll have it here. This is a coily bracket. And inside these brackets, we have the elements. The example we have here, we have a collection of fruits, and it's a set of 3 elements. We have apple, banana, and peach. So these are elements of this set, fruits. Elements of a set are separated by commas, as we can see. They are separated by commas. Set notation. Sets are denoted by capital letters such as capital letter X, capital letter Y, or capital letter Z, while the elements are usually denoted by small letters. So that's how you differentiate it. For sets, you denote them using capital letters of the alphabet, but the elements, you denote them using small letters of the alphabet. Take for example, if A, B, C, D, all in small letters, are elements, and capital letter B is a set, we'll represent this information as B equal to, you place your curly brackets and inside you write A, B, C, D. So B is the set, while A, B, C, D are the elements. Sometimes a symbol E, it's not really E, but that's what it looks like, is used to denote membership of a set. This symbol is used to denote membership of a set. It is used to show that an element is a member of this set. If A, that is an element, is in small letter, if A belongs to a set X, we write it as A element of X, which means that A is in X. However, if A does not belong to X, we'll write it as A, you stroke the E. So you can see here, this is denoting not a member of. When you write the E, and you stroke it, it means not a member of. So when A is not a member of X, we write it as A, not a member of X. Given that A is equal to 4, 5, 6, 7, and B is equal to 1, 8, 9, 10, then we can say that 5 is an element of A, because 5 is in A, Also, 10 is an element of B, 10 is in B, but 10 is not an element of A. 10 is not an element of A. You stroke the E, not an element, because 10 is not in A. So we take the correction here. We look at some symbols used in sets and their meaning. So we have the E, as we've just talked about, denoting element of, and when you stroke the E, you have not an element of. We have what looks like C, it's more like this, denoting subset of, and when you stroke it, you have not a subset of. And when you put a kind of an equality sign below, something like this, you have a subset and equal to. We'll still get to this symbol when we'll be dealing with subsets. And then this U denotes union. That's union can also mean or. And then when it's like this, it's a little bit like N, don't mind my drawing, means intersection. That's and. And then A hyphen, that is A prime, not A. That is an element that is not in A, but it's in the universal. We'll get to that when we'll be talking about complements of sets. And then when you have a 0 and then you stroke it, we have something, we'll call it an empty set. Empty set, this is the symbol. And then we'll have that N is equal to set of natural numbers, Q is equal to set of rational numbers, R is equal to set of real numbers, and that P is equal to set of prime numbers. Z is the set of integers, E is the set of even integers, and O is the set of odd integers. So when we know these symbols, we can interpret a set, a given set question or anything, we can interpret it correctly using these symbols and these notations. We go into the types of sets. Number 1, we have universal sets. A universal set contains all the elements that can be used to solve the problem under consideration. So, a universal set is that set that contains all the elements that can be used to solve the problem under consideration. So, the universal set is represented by two common symbols. We have this E and U. E in this case is no longer element of. This E stands for universal set. You can also represent it with the formula U. E or U can be used to represent universal sets. Consider the sets X equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is, X is a set of numbers 1 to 10, positive integers, while Y is a set of 4, 6, 8, 10. Z is a set of 3, 5, 7, 0. The universal set in this case is X because it contains all the elements that can be used to solve this problem that we are considering now. So X contains numbers 1 to 10. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is the universal set in this case. Finite sets is another type of set, and this is a set whose elements can be listed. The elements don't run into infinity, like you can count them and you can list them. That is, they have countable number of elements. So when a set has countable number of elements, you say that the set is finite. For example, a set of states in the southeast zone of Nigeria is a finite set. The states in the southeast zone are Abia, Anambra, Ebonyi, Enugu, and Imo states. So to represent it, you have S to be the set of the states in the southeast zone, and we have the curly brackets, and inside we have Abia, Anambra, Ebonyi, Enugu, and Imo. So this set of states in southeast zone of Nigeria is finite because you can list them. When we get to infinite sets, we will see the difference between finite and infinite sets. Still on types of sets, infinite sets. This set is made up of uncountable number of elements. Uncountable number of elements. The elements that make up the set is uncountable. Example is the set of all positive integers. So you can count and run into millions and you are still counting. So it is uncountable. We say that it is a finite set. So a set of positive integers is a finite set. Is an infinite set. The elements are uncountable. Another type, subset. If all the elements of set B are members of set A, that is, all the elements of set B are in set A, then B is a subset of A. I'll take it again. If all the elements of set B are members of set A, then set B is a subset of A. So you use subset when the set in question is a member of another set. So if all the elements of set B is in set A, that is to say that set B is a subset of A. For example, if A is equal to 2, 5, 8, 9, and B is equal to 2, 5, therefore B is a subset of A and is written as BCA. This C here should be more like this, denoting subset. So it should look like B subset of A. This means B subset of A. The notation for subsets is C. It's looking like this. We've talked about this before. The notation for C, don't mind my drawing. In the above example, B is a proper set. So we'll see the reason why we say that B is a proper set. This is because A contains B, but B does not contain A. In which case, A is not equal to B. This trick is supposed to be here. We're supposed to have A not equal to B. So because A contains B, but B does not contain A, that is to say that A is not equal to B. So we say that B is a proper subset of A. A contains B, that is set A contains set B, is noted by this symbol. This symbol we have here. When it's written like this, A, inverse of C, I'd rather call it that, B, means that A contains B. That is what this symbol stands for, contains. But if A contains B and B also contains A, in which A is equal to B, then each set is an improper subset. Each set is an improper subset of each other. This is symbolically represented as A. Sorry, this is not supposed to be here. It's supposed to be A is a subset and equal to B. A is a subset and equal to B. That is this symbol. If you remember when we were talking about symbols, we saw this symbol and it means subset of and equal to. We continue still on subsets. The number of subsets a set can have is given by 2 raised to power n, where n is equal to number of elements in the set. So to calculate the number of subsets a set can have, you just count the number of elements in the set. Say there are 4. So therefore, the number of subsets the set can have is 2 raised to power 4, and that will give you 16. So that is how you calculate the number of subsets a set can have. This number contains two improper subsets for all sets except the null set. This number contains 2 improper sets for all sets except the null set, whose only subset is improper. That is, the null set, its only subset is improper because it will be equal to it. Remember that improper subsets arises, or improper subsets are sets in which the set A and B contain each other. So they are equal. So you say that they are improper sets. So for a null set, that is a set that has no element, each subset will be improper. That is, it will also have no element. So for example, a set containing 3 elements has 2 raised to power 3, which is equal to 8 subsets, 2 of which are improper, leaving 6 proper sets. Example, write down all the subsets of the set A. Set A has 3 elements, so it will have 8 subsets. Here, n is equal to 3. A will contain 2 raised to power 3. Sorry, this is 2 raised to power 3. It is equal to 8 subsets. They are 2. This is 1. Another subset, 2, 3, 4, 5, 6, 7, and then 8. So these are the 8 subsets, of which 2 is improper and 6 is proper out of these 8. Empty set. Another type of set. This is a set that has no element in it. No element at all. It is usually written as curly brackets containing nothing. That is, this is it. Or it can be denoted by this formula. When you write 0 and you cross it out, you have this formula. Sorry, this symbol. So you denote empty set using this symbol or this symbol. Note that a curly bracket containing 0 inside as the element, that is this, is not an empty set because 0 is considered to be an element. So when you have your curly bracket and you have 0 inside, the set is not empty because it contains an element, because 0 is considered to be an element. Empty set is otherwise known as null set or void set. That is a set that contains no element at all. Examples of null sets are A. A is a set of flying cows. We know we don't have flying cows, so there will be no element in A. So A is an empty set. Okay, another one is B. B is a set of pregnant men. We know that men don't get pregnant, so set of pregnant men will be an empty set because there will be no element in it. Also C, set of human beings with 2 heads. This is 2 heads. This is also impossible, and there will be no element in this set, so C is also an empty set. So these are examples of the 3 examples of null sets, that's empty sets. Equal sets. 2 or more sets are said to be equal if they have the same elements in them. So if set A and set B have the same element in them, they are equal. Take for example, set A is 1, 2, 1, 2, 4, 5, while set B is 2, 1, 5, 4. Then A and B are said to be equal. That is, A is equal to B because they contain the same elements in them. We say they are equal sets. Equivalent sets. Two sets X and Y are equivalent if there is one-to-one correspondence between the elements in the two sets. Example, set X is boy, girl, man, while set T is contains elements A, B, and C. We say that set S and set T are equivalent. They contain one-to-one correspondence. Disjoint set is another type of set. Two or more sets are said to be disjoint if they have no elements in common. No elements in common, we say the two sets are disjoint. Consider the following sets L, which is B, D, F, G, Z. That is, L contains elements B, D, F, G, and Z, while set M contains A, C, E, and I. And as we can see, set L and set M has no element in common, and so they are said to be disjoint. Cardinality of a set. The cardinality of a set is the number of elements in a set. It is simply the number of elements in a set, and it is denoted by any bracket A. That is, it could be any set. When the set is B, then it will be any bracket B. So any bracket, the set, number of sets. A set without an element has a cardinal number of 0. A set with only one element is called a singleton or a unit set, and its cardinality is 1. That's a set with only one element. For example, given set M to be A, B, C, D, E, find the number of elements in set M, that is n bracket M. Solution: M is equal to A, B, C, D, E. The number of elements in M is equal to 1, 2, 3, 4, 5. So the number of elements in M is equal to 5. We'll now go over to operation on sets. We are done with the types of sets. There are 4 operations on sets, namely 1. Differences, 2. Complement, 3. Union, 4. Intersection. We are going to take on these operations one after the other. We'll start with difference, that is difference of two sets. Given two sets A and B, the difference of A and B given by A minus B is the set of all elements in A but not in B. All elements in A but not in B. And 2, B minus A is the set of all elements in B but not in A. A minus B is all elements in A, not in B, while B minus A is all elements in B, not in A. So A minus B is in A but not in B, and B minus A is in B but not in A. Example, let A be equal to 3, 5, 1, 6, 9, and B to be 7, 8, 3, 2. A minus B is equal to 5, 1, 6, 9. That is, 5, 1, 6, 9 are in A, but are not in B. B minus A, elements in B, not in A, we have 7, 8, 2. 7, 8, 2 are in B, but they are not in A. We look at complements of a set. The complement of a set is defined with respect to a given universal set, E or U. This is the symbol for universal set. The complement of a set is the set of all elements in E, that is in the universal, but not in A itself. It can be considered as the difference E minus A, that is in the universal, but not in A. We are assuming that A is the set you are dealing with, while this E is the universal set that contains all the elements that are in consideration in a given problem, as we've defined it before. So the difference E minus A are all the elements in the universal, but not in A. The symbol AC or A prime, that is A hyphen, is used to denote the complement of a set A. Example, let E, that is the universal set, be set of numbers between 1 to 10. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. While A is a set of 1, 2, 5, 6, 9. B is equal to 3, 8, 4, 7, 1. Then A prime, that is complement of A, are the elements that are in the universal but not in A. When you list the elements of the universal set, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the elements of the universal. So A is 1, 2, 5, 6, 9. The elements that are not in A but are in the universal are 3, 4, 7, 8, and 10. While B prime, that is complement of B, elements that are in the universal but are not in B, we have 2, 5, 6, 9, 10. So that is how you check your complement of a set. When you're asked to find the complement of a set A, given that A is 1, 2, 5, 6, you go to the universal set, you list out your universal set, and you check out for those elements that are in the universal but are not in A. The union of two sets. The union of two sets A and B, written as A union B or B union A, is the set of all elements either in A or B or in both. So they are all elements either in A, in B, or in both. Note that in A union B, no elements must be repeated. So when you merging the two sets, no elements should be repeated. For example, if A is equal to A, B, C, D, E, F, and B is B, C, M, A union B is equal to A, B, C, D, E, F, M. Because B and C is already in A, there is no need to repeat them. So you take the elements 1, 1. No elements should be repeated. So we take some notes. Still under union of two sets. N, that's the number of set A, N bracket A, is equal to 6. That's from the examples we just looked into. And the number of B is equal to 3. But number of A union B is equal to 7. We are still talking about the example we just dealt with. And not equal to 6 plus 3. So when you are dealing with union of sets, you don't just add up the elements of the two sets. You have to check out for the sets, the elements the sets share in common, and you are not supposed to include an element twice. So because two elements B and C are common to both A and B, that's both sets A and B, that is why the union of A and B, the number of A union B, that is the number of A union B is equal to 7 instead of 9, because B and C was repeated, B and C is in A and also in B. So there is no need repeating B and C. That is why we have n number of A union B to be equal to 7. Both A and B are common to both A and B. Each element in A or in B is also in A union B. So all the elements in A and all the elements in B are in A union B. Two elements common to both A and B are also in A union B. No element in A union B is repeated. Note that. And that n, that is number of A union B, is equal to number of A plus number of B minus number of A intersection B. This is it, A intersection B. That is, those elements A and B have in common. You have to subtract it from the sum of number of elements in A plus number of elements in B. Union implies OR, which is synonymous with addition. That is why we add. But remember to subtract when there is intersection between the two sets. That is, where in a situation whereby between the two sets have some certain elements in common. AUB is read as A union B. Intersection of two sets. The intersection of two sets A and B is another set, C, which contains the elements common to the two sets. I read it again. The intersection of two sets A and B is another set, C, and this C contains elements that are common to the two sets. So when you have a set A and B, you list out the elements that are common to A and B, and that will give you this another set C, which contains all the elements common to both A and B. The symbol N is used to denote intersection of two sets, and this symbol is read as intersection. So when we have A and B, we have A intersection B. A intersection B. Example: let A be equal to A, B, C, D, E, F, and B be equal to A, I, E, O, U. Find A intersection B. So we'll look out for the elements A and B have in common. Solution: A, B, C, D, E, F. B is equal to A, I, E, O, U. A intersection B, therefore, is equal to A and E, because it is only A and E that these two sets A and B have in common. So A intersection B is equal to A, E. So we now look at how to use inequality sign to define a set. Remember the meanings of the following symbol. This symbol is for greater than, this is for greater than or equal to, this is for less than, and this is less than or equal to. So we now apply what we've learned so far to solve some examples. Example 1. List members of the set A. We have that A is equal to Y such that 1 is less than Y, less than equal to 6, and that Y is an element of natural numbers n. Solution: n means natural numbers, that is positive whole numbers. So we have that a is equal to y, and that y is less than 1. Sorry, 1 is less than y, and y is less than equal to 6. That is to say, y is greater than 1, but y is less than 6, less than or equal to 6. So that means y lies between 2 and 6. This is read as a is a set y such that 1 is less than y, and y is less than or equal to 6. Therefore, a is equal to 2, 3, 4, 5, 6. So to answer this type of questions, you have to know your inequality signs. When you know that this stands for less than, and that this stands for less than or equal to, you can interpret the question and so can be able to answer it. And remember these symbols n that we talked about at the beginning. You have to know them so that when you see these symbols, you will know what they mean, and so you can be able to answer the questions. Example 2. List the elements of the set P such that P is equal to X. List the elements of set P is equal to X such that -2 is less than X, less than equal to 5, and that X is an element of integer. That's integer numbers. Have solution. P is equal to X such that -2 is less than X, less than equal to 5, X element of Z, that's integer. And you know that integer is positive or negative whole number, any positive or negative whole number. Here, X is strictly greater than -2, but less than or equal to 5. Therefore, the set lies within -1 and 5. We have P to be equal to -1, 0, 1, 2, 3, 4, 5. We look at example 3. If U is equal to X such that 0 is less than or equal to X, less than or equal to 10. And we also have that U is the universal, you know. That's the universal is equal to X such that 0 is less than equal to X, less than equal to 10. And set A is equal to X such that 1 is less than equal to X, X less than equal to 4. Set B is equal to X such that 6 is less than equal to X, X less than equal to 7. So we're now asked to find A prime, that is complement of A, B prime, A union B. This is A union B. And then this is IV is A union B prime. This is for this and this is for this. So we solve. Solution. Universal universal set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is elements 1 to 10. That's numbers 1 to 10, sorry. And as set A is equal to, when you interpret it, you have that X lies between 1 and 4. So we have A to be equal to 1, 2, 3, and 4. Then for A prime, that is all the elements in the universal, but not in A. So A prime is equal to 5, 6, 7, 8, 9, 10. These elements are in the universal, but they are not in A. B, when you interpret B, you get that B is equal to 6, 7, because X is less than equal to 6, less than equal to 7. So the X lies between 6 and 7. That is why we have B to be equal to 6, 7. Then B prime, that is elements in the universal but not in B. We have B prime to be equal to 1, 2, 3, 4, 5, 8, 9, 10. These elements are in the universal, but they are not in B. A union B, that is when you mix or when you put together all the elements in A and all the elements in B. You have 1, 2, 3, 4, 6, 7. So A union B is this 1, 2, 3, 4, 6, 7. So for A union B prime, these are elements that are in the universal but are not in A union B. So since we have our A union B to be this, A union B prime will be 5, 8, 9, 10. These elements are in the universal, but they are not in A union B. We also have solved the examples still on inequalities. We have P and Q are subsets of the universal set U, defined as U equal to X, such that X is an integer and 1 is less than X, less than 15. So we know that X is an integer, and we also know that 1 is less than X, so therefore X is greater than 1, but X is less than 15. Set P is equal to X, such that X is odd number and set Q is equal to X, such that X is prime, that is a prime number, or rather prime numbers. Then we are now asked to find the number of P prime intersection Q prime. So we'll find all the elements in the universal that are not in P, and then all the elements that are in the universal are not in Q. We'll now find the elements P prime and Q prime have in common. When we find them, we'll now count them to find the number of elements in this set. So let's solve. The universal we have universal to be equal to X, such that 1 is less than X, X is less than 15, and X is an integer. So we have U to be numbers between 2 and 14. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So for P, we say that P is a set of odd numbers. So from the universal, we choose the odd numbers from 2 to 14, and we have 3, 5, 7, 9, 11, 13. So P prime, that is elements in universal, not in P, we have 2, 4, 6, 8, 10, 12, 14, the even numbers. Q is set of prime numbers between 2 and 14. So we'll select them out. We have Q to be equal to 2, 3, 5, 7, 11, 13. Q prime will then be all the elements in the universal not in Q, and we have 4, 6, 8, 9, 10, 12, 14. So P intersection Q, that is P prime intersection Q prime, the elements they have in common, we have 4, 6, 8, 10, 12, 14. That is, this is P prime and this is Q prime. The elements they have in common, 4, 6, 8, 10, 12, 14. So the number of P prime intersection Q prime is 1, 2, 3, 4, 5, 6. And we have it here. N bracket P prime intersection Q prime is equal to 6. Another example, if X is equal to N squared plus 1, and we have that N is equal to 0, 2, 3, that is, you have to find X when N is 0, 2, and 3. And that U, the universal, is equal to N plus 1. We also find N, or rather we also find the sets, the elements in the universal when N is equal to 2, 3, 5. Now we asked to find x intersection y. I think we got it mixed there. So this is y, sorry. This is y. Set y, sorry, not u. Set y. So we have to find x intersection y. Solution. X is equal to n squared plus 1. N equal to 0, 2, 3. So when n is 0, n squared plus 1, you substitute 0 squared plus 1, you have 0 plus 1, which is equal to 1. When n is 2, you have 2 squared plus 1. To give you 4 plus 1, you have 5. And then when n is equal to 3, you have 3 squared plus 1, which is equal to 9 plus 1, we have 10. So the elements in set X, that is this, the elements in set X are 1, 5, 10. The elements in set X are 1, 5, 10. The elements in set Y you calculate. When n is 2, we have that y is equal to n plus 1. So when n is 2, when you substitute 2 in place of n, we have that you have y to be 2 plus 1, which is 3. When n is 3, we have n plus 1, that is 3 plus 1, we have 4. And when n is 5, we have 6. So the elements in set Y are 3, 4, 6. So now that we've listed the elements in these sets, we'll now go ahead to check for x intersection y. So elements in set X 1, 5, 10, and elements in set Y 3, 4, 6. As we can see, they have no elements in common, and so the set x intersection y is an empty set. It has no element in it. So that is why we say it is an empty set. And with that, we come to the end of this section. In section 2, we'll continue with Venn diagram.